Hello, I'm Doug, StandUp Physicist. And today I'm going to sell you the very t-shirt I'm wearing right now. Hey Einstein, you're in my way. I've always wanted to say that. It says, the stand-up physicist, that's me, said 0 equals del squared phi equals the second time derivative of AI minus the second spatial derivative of AI with respect to xj minus the second spatial derivative of AI with respect to xk. And there was light, gravity, radiation, a nucleus, but no stinking Higgs. Well, I will eventually explain what most of this means, even the Higgs, which happens to be a particle that folks need. But there's more, and it's written right on the back. I can't see if you can see that or not. Oh well. An act of faith. It says one. Oh, you probably don't know what that symbol is. It's a symbol for Lagrangian. One Lagrangian to rule them all. J.R.R. Albert Tolkien. Well, actually, there was a J.R.R. Tolkien, and there was an Albert Einstein, but there was no J.R.R. Albert Tolkien. Somebody had made that quote up. Then 4 lines of scary-looking math. And there is also something at the bottom, something about quaternion product and hypercomplex product. I really am going to spend a large amount of time explaining everything that is on this particular t-shirt. I mean, it's not like that t-shirt, Lauderdale, sex, sun, sex, booze, and sex. I mean, I've never been to Fort Lauderdale, but that sounds like fun for the entire family. Well, maybe not the entire family, but this t-shirt is going to take quite a bit of effort to explain, but I think it's darn well worth it. Stop what you're doing right now, because this t-shirt just costs $15 plus $3 for shipping and handling, which makes $18 total. So go to the URL on your screen now, hit the pause button. I'll wait. That address is bit.ly, capital GEM t-shirt. What could be simpler? Okay, you're back? Oh, well, I'll go on even if you didn't buy the t-shirt. That's okay. Maybe you want to understand a little bit more before you buy. You're being a smart shopper. There are not that many t-shirts that deal with field theory. In fact, I can only think of one that had any popularity. It says, and God said, and then it has the Maxwell equations, and there was light. And that does describe how light, electricity, and magnetism all interact with each other on Earth as it is in heavens. The math on this t-shirt has greater ambitions. And that is because it's trying to unify not only light, but the 4 known forces of nature. That would be the electromagnetism, the stuff of light, gravity, the stuff that keeps you here, the weak force, which has to do with beta decay, it's a type of radiation, and the strong force that keeps the nucleus together, because the nucleus has a bunch of positive charges that don't want to hang together, except the strong force is that strong to keep them there. And as far as we can tell, we've kind of looked for other forces, haven't found any. So it looks like that's kind of a complete picture. And this shirt at least tries to do them all. Physics already has a somewhat unified field called the Standard Model. And the Standard Model unifies electromagnetism, the light stuff, with the weak field and the strong field. But it's just too complicated to fit on a t-shirt. The fact that gravity does not work nicely with the other three is like so odd. Because when you first learn about physics, one of the first laws you're going to learn is Newton's law of gravity. And that is F equals minus G m over r squared. And a little while later, they usually introduce you to Coulomb's law, which is F equals K. Oh, actually, there's some variation on a K thing, but it's a constant. So if you have a different collection of letters, it really doesn't matter that much. One electric charge Q times another electric charge Q over r squared. And you go, okay, so different constants, G versus the K thing. Different charge, mass kind of thing versus electric charge. And, oh yeah, one's got a minus sign and the other one doesn't. I mean, those are so similar, it shouldn't be that hard to get them together, right? Well, efforts have been going on since the mid-1700s to get them to go together, and they've resisted everything. That's rather amazing. I want to give you a little bit of the backstory here because it's kind of fun. So you recognize this guy? All right? That's right. Big old Ben. Hope you keep a lot of these at home. So Ben was studying electricity like at the start of figuring this stuff out. To give you a sense of how early on he was, this was before Luigi Galvani, he was Italian, can you believe it, with a name like that? Invented the battery. So in order to do his experiments, he had to rub his feet against the carpet. Except in Franklin's time, there weren't any carpets. You know, he had to rub some things like rabbit fur, or yeah, it was the age of fur. So he had rabbit fur and stuff and got generated electricity that way. And he did a bunch of experiments to try and figure out the qualities of this stuff. And he was talking to Joseph Priestley, who was the guy who got most famous for figuring out that there's oxygen in the atmosphere that keeps us alive. Okay, somebody had to figure that out, and that was the Priestley fellow. But it was a time when you not only did that, but you did all kinds of other science stuff, and you probably dabble a little bit with religion if you were in the mood for that sort of thing. And Franklin described this one particular experiment, how he had this hollow sphere, and he put an electric charge on it, and then he looked on the inside, and he didn't see any charge, and any electric field inside. And Priestley said, Newton said the same thing about gravity. If you've got a shell, a massive shell, and if you're on the outside, there's going to be a gravity field. But if you go on the inside, because it's an inverse square law, it nicely cancels out. And so Priestley just jumped to the conclusion that electricity must be governed by an inverse square law. Now, he was right in his jump, but Coulomb gets the credit because he went into the lab and did careful experiments to show, all right? But I just bring up that story because it shows that as soon as people started thinking about electricity, they also started thinking about gravity and the relationship between the two, and it was useful to do. It actually made this major insight into how electromagnetism works. So this link between gravity and electromagnetism is before the Revolutionary War for the United States. This problem has been around for a long time. It must be tricky. Actually, it must be super sneaky tricky. All right. The reason I kind of put it in that category is the observation that the smartest people on the planet seem to be attracted to studying physics. So you get the very smartest people figuring out, studying the same thing. They know this problem's around since like day one of electrostatic theory, and they haven't solved it yet. It's like that there has to be something super sneaky going on here. And so my super sneaky tricky idea is that there's really more than one way to multiply. I mean, smart guys learn the rule for multiplying numbers together. If you've got a vector like this, and you multiply by another vector like that, then you get a third vector, and like that. And they go, okay, and I look at that in a mirror, and boom, my math better have that kind of property. And they can cite like tens of thousands of places where this is a confirmed. Nature uses this right-hand rule, this cross product. It uses curls to describe so very many things. But I think that what nature does is she's tricky. She not only uses this, but she uses another type of multiplication that actually hides that doesn't have this, you look in a mirror and it looks different property. I mean, if this was a plane and this is another plane and I look at that in a mirror, it's actually going to look the same. So there are things out there that because of their symmetries, whatever, you look at them and they do look the same in a mirror. And I think nature must be doing some kind of trick like that. But I can actually be more specific about what's shown on this shirt. But that's the core idea, that there is another type of multiplication out there that's much more symmetric. And that's what's needed to describe gravity. What standard physics has is the standard model. That explains these three forces, the weak force, the strong force, and light, as symmetries and conserved charges. One implies the other. It's really kind of cool. And the standard model is really great, except for one huge problem. And that is nothing in the standard model has any mass. Oops. I mean, that's obviously not the way it is. Okay? So you gotta deal with this kind of a problem here. You must somehow figure out how to put in mass without messing up the symmetries. Why is that? Because if you mess up the symmetries, then that actually messes up the conservation laws. And what we have done in the lab is shown to a very high degree of precision that electrical charge is conserved. So if you break the symmetry of electric charge, then you don't have to conserve electric charge anymore. All right? So you really have to absolutely preserve that symmetry no matter what. Enter the Higgs mechanism. It is a Mexican hat trick. Oh, this is not a Mexican hat. Okay, we're going to have to imagine. Okay, maybe I'll get a picture of. I actually don't own a sombrero. I don't. It's just the way things are. It's not so good for swing dancing. I think that's the real reason. So, what the Mexican hat represents is that the vacuum state for all massive particles is a false vacuum. That means that zero isn't quite zero, it's above zero, and that it spontaneously goes down to the real zero, okay? The rim of the Mexican hat. And And it's the Higgs particle that, does this false vacuum kind of job. So that will be able to preserve all of the symmetries of the Standard Model without breaking a darn thing. So all we need to do is detect the Higgs. And we've been searching for it for about 10 years, and we haven't found it. That's a bit of a bummer. In fact, it is so important to physicists that they've set up an experiment to try and detect it. Now, that experiment cost $10 billion to set up. It's called the Large Hadron Collider, or LHC, and they're going to see if they can spot the Higgs. Because the Higgs is really the only way the theorists have figured out how to keep the symmetries in 3 out of those 4 known forces while adding in a mass. And actually, there's another reason why they want to do this, and that is because they're trying to get gravity in with the rest of the forces, and the only way they can figure to do that is to find these super partners where everybody on the dance floor has a partner that has yet to be seen. Okay? So this is the Great No-Seeums experiment. We haven't seen no Higgs. We haven't seen no neutrinolos, or whatever they're called, no superparticles. And we're investing this so that we can see all these sorts of particles. Well, the StandUp Physicist, I want to tip my hat to the folks at the LHC, and I wish them the best of luck in their great experiment. It's really quite the mission. But I don't believe in false gods, and I don't believe in false vacuums. I think that what is on this t-shirt, if you understood that, you would say there's really no need for the Higgs particle, nor is there a need for a single supersymmetric particle. So this, it's this t-shirt versus the LHC. They're going to win, okay? Unless some of their theory guys kind of download my technical papers and confirm that the math is correct and possibly even interesting. So I just think this goal of getting the Higgs to work out, it doesn't really actually make sense to me. Because the Standard Model, it just doesn't do gravity. We know that. That's stated, right? And yet its problem has to do with mass. So to solve that problem, you got to include gravity within the structure of the Standard Model. But the Higgs particle can't do that, because the Higgs particle is a spin zero, a scalar particle. But remember that, zero, spin zero. And our best theory for how gravity works is involves a spin 2 particle, the graviton. And since 2 doesn't equal 0, I don't see how you're going to mesh those two. And I think what they would say is something like, oh, those are 2 different kind of areas. One is about particle mass, and the other is the actual effect of gravity. It's like, but to me, it rings hollow. Your way of bringing in mass should bring in the field equations, and the Higgs never did that. It just fixed up brilliant shortcut, a problem with the Standard Model. It didn't bring in mass in a nice way. So what is the fundamental difference between gravitation and, say, just electromagnetism? Well, gravity is the I love you force. No matter where you are, no matter who you are, no matter what your convictions are. In fact, I love everything around me. It is universal. I love everything below me. I love the entire universe. Although I got a bias. I love things that are closer to me more than anything else. That's the inverse square kind of things. It's kind of love the one you're with. It's a very 60s ideal. That is what gravity is. Now, what electromagnetism is like so much more passionate, okay, in the love of opposites, okay? Very heterosexual here. I'm not saying that gravity is the gravity, there's only love. There's no gender, okay? I want to stay away from that. No gender, okay? But when you get to electromagnetism, there's a positive and a negative, and the positive and negative, they love each other not just a little stronger, not 1,000 times, not 1,000,000 times. No, that's small scale. 10 to the 42 times stronger is the passion for opposite charges electrically. I mean, it's actually an issue I don't get. Even though I have a unified standard model theory, I don't get why it's so berserkly different in its intensity, but it is, okay? But it's not only love. I mean, they frickin' hate each other, okay? You got the same charges, you are not in the same neighborhood. Unless you're, you know, really being held together by the strong force, which is the ultimate dominatrix if there ever was one. But, yeah, this total passionate, super passionate hatred. And the third option, there's always the third rail, and that is you just don't care, like, at all. Neutrality. Someone who's a eunuch. It's like, look, hey, it doesn't matter to me. I'm not participating. I have no electric charge. I will not pay attention to any of you, sorts of things. And that's really remarkable. This fundamental difference of the universal attraction, no matter how super weak it is, and the love, hate, or not care. And I think you really have to build that, construct that into your fundamental accounting system, or you're not going to have a chance at getting universal love together with light. So my idea is that the product, the multiplication kind of product needed for gravity to be the universal love force must have 0 minus signs in it. With no minus signs, it can only be positive. And in fact, this is known as the California representation of hypercomplex numbers. Since everything is sunny and positive, of course I've never been to California, but yeah, lived in California. I think I visited there once, right? And the California representation of hypercomplex numbers, I'm not sure if it's ever appeared in the literature. Hypercomplex numbers, sure, but not this all positive all the time kind of thing. Other forces are actually going to need the sign flipping, like electromagnetism. It's definitely going to need that sort of thing. So on the back of the shirt, the stuff with the box times sort of symbol in there, that is the gravity stuff, universal love kind of thing. And electricity and all the rest is going to be in the ones that don't have that little box squared sort of thing. So now I'm going to do my standard Lagrangian riff. If you've watched my other videos, then this should be familiar. But if you're new to this, I hope this is clear enough to you. A Lagrange density is every way that energy can be traded inside of a box. The action is now the integration, in other words, the addition of the Lagrangian over a volume and time. So what you get back when you do the action is an energy times an arbitrary amount of time. Well, why would anybody do this? Why would anyone do that kind of sum? Because they could sum it over a second? They could sum it over 1,000 years. Well, because the real game is to take that Lagrangian and say, what can I change in there? And then not change the integration, the sum, after some fixed amount of time, whatever that amount of time happens to be. Because if I find that thing that I can change without changing this integration, then what I have found is something that will be the same. It's a symmetry of this action, and it will be conserved. There will be something conserved that's related to that symmetry. So if you look at the action that's written on the back of this t-shirt, you'll notice there's no like t, no time kind of thing in there. That's a symmetry. If I come back 3 years from now and I do the integral with that thing over, some set amount of time, it's going to end up being the same. And therefore, we can conclude that energy is conserved in that Lagrangian. There's no position, no x, y, z there. There are changes in position, but that's different from the actual position. Okay, so we could take this integral and we could move it over somewhere else, and as long as we integrate over all the space, some over some amount of time, we're going to get the same answer. And that actually indicates that linear momentum is conserved. And then you notice that, well, there are no angles in here. No thetas or phis, that sort of thing. And that's a symmetry of the action. And therefore there is a conserved quantity. That conserved quantity is known as angular momentum. Well, we know from experiment that electric charge is conserved, weak charge is conserved, strong charge is conserved. So that means that there must be symmetries in this action that lead to those conservation rules. So the goal is to spot those symmetries here. So the symmetry underlying electric charge is known as U1, or also known as a unit circle in the complex plane. Now, a quaternion is actually 3 complex numbers that share the same real. So wherever you see like A over the absolute value of A, that means I'm normalizing A to its norm, and it means that it confines A to be on this unit circle. So it doesn't matter how I shift around that circle, I'm guaranteed to live on, well, actually 3 different circles, but there's still going to be circles. So because of that quality, we know that this Lagrangian has U1 symmetry, and therefore it's going to conserve electric charge. Sweet. Now we get on to the weak force. This symmetry that's related to that conserved charge is called SU2, and it goes by the name of unit quaternions. Now, since I'm writing this in terms of quaternions, I should be able to spot a unit quaternion. And there are a bunch of different ways that could be done. I happen to choose one that's like the exponential of A minus A star. That actually makes it depend on 3 numbers, which is great because SU3 depends on 3 numbers or charges, kind of generators, sort of things in its Lie algebra. So that's really great. You can just look at it and see U1 symmetry. Oh, that's the thing over the norm. You can see SU2, that's the exponential thingy. Well, how about SU3? Well, SU3, that depends on 8 different elements in its kind of generator algebra. And that sounds an awful lot like 2 quaternions. And, well, you could just multiply those 2 quaternions together, but you'd kind of get back the same symmetry that you started with. That's one of the qualities of group theory. If you have one thing and you multiply it by another and they're part of the same group, they're going to stay in the group. And that's why there's a little flower power symbol there, that's actually a conjugate operator, that changes its algebra just enough that this is actually a new group. It's a new group that we know is going to have it's always going to be at 1, because that's the way the math works out. But it depends on 8 thingies, and so I think that is the group away. If you take a potential quaternion potential A and a quaternion potential B, that's got 8 independent elements to it, and I think that's the way to represent the group SU3. All right, so this discussion has been incredibly abstract. So I'm sure the guy in the back is going to go, excuse me, but why the fuck does any of this work? Now, I actually think that's a great question, okay? Because if you listen to people talk about the Standard Model, they will say it has 2 big issues, philosophical issues almost. One is, we don't know why there are just these 3 forces in the Standard Model. I mean, why shouldn't there be, say, 4 or 5? There just isn't an answer to that very basic question. And there also isn't a question to why these 3 in particular. You see, because group theory has lots of different groups. Why doesn't nature use some of them? There isn't an answer in the Standard Model. Now, I think there is an answer if you use quaternions. Because if you think about it, what is an observer like you? Where are you right now? I think you right now, right now is, on my watch, is 0, okay? And you are at the center of your universe. So you're at 0, 0, 0. So that's 0, 0, 0, 0. Okay, cool. That's easy to remember. All right, now something happens. And I'm not going to be any more specific than that. Something happens to you. Actually, maybe I should say you just get older. But no, let's not say that. Let's say something. It could be from some EM thing. It could be some weak field thing. It could be some strong force thing. I don't care. Just kind of describe the situation now. Okay. So I guess you're still at the center of your universe as far as your position is concerned, right? You haven't moved, so that's still 0, 0, 0. But time has happened. There's been enough time gone by that something happened to you. So why don't we call that, just to be nice and general, 1, 0, 0, 0. So you make this big transition from 0, 0, 0 to 1, 0, 0, 0. Okay, now describe that. Okay. Well, the miracle of quaternions is that when you take one quaternion, say A, take its conjugate, and now we say that A equals B. So if A star A, where I've normalized all these things, that's going to equal 1, 0, 0, 0. Okay? So I'll be able to say, hey, no matter what went on, I don't know the details of what went on with the U1 symmetry. Maybe you shifted around a bit. Maybe something happened wacko in the SU2 part. I don't know. But I can guarantee you that you get back to 1, 0, 0, 0. There's one more type of subtlety. Let's say I measure my 1, 0, 0, 0 in the basement here. You are 1 floor above me, and you measure your 1, 0, 0, 0. And we get a third person to compare our 2 notions of oneness. And if they are really, really careful, they might actually notice a slight gradual change due to the gravitational field. And because that is what gravity does. It does this symmetric change from one kind of set of rulers to another. And it's very subtle. It has to do with gravity being so much weaker than everything else, and that changing of rulers is a very symmetric kind of operation, I think, that requires the California representation of hypercomplex numbers. I will now try to explain why the t-shirt does not need the Higgs. Because if a particle travels at the speed of light, it must be invariant under a gauge transformation. Whatever that means. Well, at least photons are like that, gravitons are like that, gluons are like that. And the kind of corollary to that is that if you have a mass, which like virtually everything else does have a mass, then you must be gauge dependent. So this has got to be really kind of tricky, because you must be able to say that in part of your Lagrangian, it's gauge dependent, so that's where the massive particles live, and yet overall it's gauge invariant, because that way the photons and gravitons can do their work. You must have your cake and eat it too. So how are you going to pull that one off? You see, that's why the Mexican hat trick was so attractive. But with my equation, what you do is you look at it and you say, are there gauge terms here? And when you have a del act on an A, you're going to get a gauge term. And when you have A and act on it with a del, you're going to get a gauge term. In fact, the same gauge term. And if you've got a del and you've got one of these hypercomplex multipliers sort of in there, and A star, you get a gauge term, the same gauge term. And then if you do the del, take the conjugate of the del, then do the hypercomplex product with an A, you get the same gauge term again. So if you look at just the thing that was the quaternion product of del A del, and actually construct field equations out of that, you actually get to the Maxwell equations, okay? But it depends on a gauge. So it applies to massive particles. And then you've got that hypercomplex sort of thing, and if you put that through the machinery of mathematical physics, you'll end up with field equations that look awfully darn similar to Maxwell, except that you'll flip the sign on a Gauss's like law, which rocks, because Gauss's law implies that like charges repel. So flipping the right sign there gets like charges to attract, which is what happens in gravity. And it doesn't have that cross product. It has this kind of more symmetric notion of a curl. And so that's kind of cool too. So together, those two things definitely depend on gauge. They definitely apply to things with mass. But the gauge term here is, we'll call it G squared. And the gauge term for the ones with a hypercomplex product, also G squared. But we're subtracting them. So G squared minus G squared is nothing. So separately, they will apply to things that have mass. And yet overall, it's going to be mediated by particles that that can travel the speed of light, because overall it's gauge invariant. So that's how I do my own trick to get around it. So enough about the back of the t-shirt, which is kind of scary to look at, all right? The question is, how do you get to the front of the t-shirt? Well, you get to the front by using something called the Euler-Lagrange equation. It's a math machine, okay? You feed it a Lagrangian, out comes the field equations every single time. And I actually have a video that's devoted to doing that in detail. I like to say that it's kind of like a Sudoku puzzle, in the sense that there are not that many rules, but you got to follow them, and there's a lot of detail to keep track of. But if you do, you'll actually be able to derive the Maxwell equations. And that is worth the time and effort. I mean, to be able to say, I know why God said that. It's kind of cool to be able to do that. And then you'll be able to see I'm doing just a couple minor variations. Well, they're not minor. They flip some signs. And you'll see the consequences of those particular sign flips and where they all go. And I don't know. I think it's really kind of neat to see it play out in detail. Now, people well trained in field theory will scratch their heads and go, I don't get this, what's written on the front. I mean, let's just start with 0, okay? That doesn't seem right. And here's the thing. It's very common for the highest level of professionals. You know, if they say, that doesn't seem right, they've got a criticism, it's a sound criticism, and that's kind of like the end of the discussion. You can't say, well, let me explain this to you. They're like too busy. They're just really too busy to sit and listen. Since you're this far into the video, this 0 rocks, okay? For the following reason. I'm trying to get gravity to get along with electricity and the weak force and the strong force, all right? Well, like charges attract for gravity and they repel for EM. So if I had a current density, then I'd have to have charges that both attracted each other and repelled each other. Doesn't make no sense. So it's good that this is 0. In fact, it's the only logically consistent thing that could have happened. And by the way, I didn't think of this first. I got the Lagrangian first and said, well, that subtraction wipes out the current density. I guess this is 0. What the heck does that mean? And then I realized, oh, that's the only thing I could have hoped for if I thought about it ahead of time. And that's kind of the way I work. Look and go, wow, is there a way to explain this? But here's another cool observation, and that is that I think lots of things are actually dipoles. Now, when we normally use this, we think of there being like a plus charge here, a little bit of distance, and a minus charge there, okay? But an electron can be viewed as a point charge dipole. Because it's saying to another electron, I love you from gravity, not very much, by the way, really kind of weak, and I hate you, totally, despise you because of electromagnetic repulsion. But it's got both attraction and repulsion of the same charge, and it's a point particle. Now, when I think about what the math of that's going to be, I mean, it scares me. And I just think it's cool that I've come up with a little bit of math that just frightens me. Somebody else is going to have to figure that one out. I don't think I got the intellectual horsepower to, but that's okay. That's okay. Another thing that's going to bother the well-versed in these kinds of arts is that they look at that and they say, you know, that looks an awful lot like the Maxwell equations in the Lorentz gauge. What is this gauge thing? Well, this gauge thing is something you can write a whole big, thick, graduate level book on because of all the deep meaning it has for Lagrangians. Now, Lagrangians, remember, you can't really detect them. You just take these, put it through the Euler-Lagrange, and you get these field equations. So there are these really difficult to understand books on gauge theory in Lagrangians. Well, the cool thing is that I've got field equations that have that same property. What's missing here is not only the charge, because I can't love and hate at the same time, but the terms that are missing here are exactly the gauge terms. So not only is my Lagrangian gauge invariant overall, remember it has parts that aren't if you look at them in isolation, but overall is gauge invariant. The field equations themselves are gauge invariant. And I don't know, that's got the ring of truth to it. You know, when you find something like that, it's like, wow, that's cool. That's cool. Now, the cynic will reject this work That's the way cynics are. They have enough experience with crappy physics to know not to look for it on YouTube. This work is not going to be posted, for example, at the preprint server, preprint archive, because those folks have enough experience with crank physicists to know it's just not worth anybody's time to really look through. And I don't have the credentials to post there, so it's just simply not going to get there. Now, the skeptic is going to be every bit as doubtful as the cynic. The difference is that the skeptic would say, well, if you have something well-formed that I could investigate, then I will put in a little bit of effort to check it out. And the URL on your screen now is at least my effort at outreach to skeptical physicists. It's a Mathematica notebook where Mathematica is a piece of amazing software that can do all this super fancy math, okay? That actually gets from what's written on the back to the field equations on the front. And to me, that says an awful lot. Okay, I do a lot of other things. Okay, but this is just a part of my technical paper. But it's really the core of it. Starting from a complicated Lagrange density and getting to really very simple looking field equations. And I know that somebody just seeing the front who's trained go, it can't be that simple. It's like, then look at the back, okay? Tell me how much you've done with quaternions and with the California representation of hypercomplex numbers. Look, I know you probably have done little with quaternions and certainly probably have never heard of hypercomplex numbers. So, but I know that I can spot them. So let's get the big picture here. This shirt is trying to do more than any other shirt in your entire wardrobe. It tries to cover the 4 known forces in the universe that govern anything that can happen in the universe. On the back, it's got the symmetries of light, and hopefully you can spot it. It's the A over the norm of A. You can spot the symmetry for the weak force as that exponential. You can spot the symmetry for the strong forces being the AB thing. All right? You can spot the stuff that does the work of, like electricity, because it involves the quaternion multiplication. And the stuff that does gravity, the universal love force, that has to be the box times kinds of stuff. And because we've got that subtraction in there of terms that are about gravity and the other about electromagnetism, that's why we don't need the Higgs. And most importantly, I think about this shirt, is that it's black, which is like the coolest color, okay? So I hope to see you wearing this shirt on the streets, and I thank you very much.
All the girls in the classroom think he's hot. He shows up wearing the sandals with the white socks. He hears them giggling while he's got his back to the class. He thinks he's got an eraser mark on his ass. And all the girls from the hall show up to hear him talk, even though most of the time he's covered in chalk. Math prof, rock star. Math prof, rock star. Oh yeah. Math prof, rock star. He was young, he never thought that he would be a math prof, rock star. And after hours outside of his office, there's a line waiting full of girls who want to ask about their quadratic equations. She leans over the desk and twirls a pencil in her hair, complains the grade he gave her was way unfair. And all the professors, they laugh about it and they wish him well. The guys in the class are all just jealous as hell. Math prof, rock star.
Hello, I'm Goldilocks. And according to the DSM-4, that's the Diagnosis and Statistical Manual for Mental Disorders, I have PLB syndrome. Picky Little Bitch syndrome. It was actually named after me. The doctor who gave me this diagnosis, he has like a BMI of 26. That's a body mass index, that's just a little bit overweight. Except I can't stand anybody who's got a BMI of like over 24. And that means like I can't ride any buses. And it's actually really hard for me to go to a doctor's office because usually the medical receptionist has a BMI of 52. I think that might be a requirement. But I'm trying to cope with that. And I was watching this video and very concerned actually, because if I go into a coma because it's so boring, then I stay there for like 10 years until some pervert comes along and kisses me, and then I have to marry him, But I found enough stuff kind of going on that I was able to stay awake. And I was thinking about other people in my condition. Would they buy this? Should they buy this t-shirt? I mean, what are the choices out there? So that's what I'm going to do here, is show you some of the choices you have in shirts that have a lot of field theory claims on the front and the Lagrangian on the back. And so I went to the Coop at MIT, and for $17.98, I got this wonderful t-shirt that says, "And God said the Maxwell equations, and there was light." Well, that's very good. But I was very concerned because there's nothing on the back. Oh my goodness. I said, I have to come up with what goes on the back. So I put on my thinking cap. And I realized this is what it should say on the back. One baby of a Lagrangian, James Clerk the Stud Maxwell. It goes b squared minus e squared plus b dot e. And the b squared minus e squared, that'll give you the source equations, and the b dot e will give you the homogeneous equations. So that's, spot on, but it's still too small because it only covers light. What about the work on gravity that Einstein did? His shirt would look like this. And Einstein guessed what Hilbert showed. That is the Einstein field equations, and there was gravity and nothing else. Now you may be wondering who that Hilbert fellow is. Well, that's revealed on the back. One brief Lagrangian, David Hilbert. It just equals R. You see, Einstein literally guessed the equations on the front in order to conserve energy, I believe. And it was Hilbert that did it the right way, because Hilbert was just an amazing mathematician. And so he did it the right way. But how could it just be one letter? I mean, isn't that a joke? I think it is in a way, because this is like the hardest thing to understand still today. When it really is tough stuff. And it involves taking the Riemann curvature tensor, which is a rank 4 tensor, which is the difference between two connections, which is derivatives, second order derivatives of metrics and stuff. And then you need to contract that once to get to the Ricci tensor. And then you need to contract that again to get to this Ricci scalar. So there is so much in there, it's really hard to grasp. But this is clearly too small. I mean, how is this work on gravity going to get along with anything else? And so far, it hasn't. And I think the back of the shirt makes it obvious why it's too small. So how about this work in the 60s and 70s to try and unify, the electromagnetism, the weak force, and the strong force? Well, they've got a t-shirt too. And it would look like this. And Salim, Glashow, Weinberg, Higgs, and some others Oh, there's really too many equations to write, even for me. And there was light, no gravity, radiation, and a nucleus, and hopefully a Higgs. They really are spending an awful lot of money to find that Higgs, so let's wish them luck. Now, on the back, it would say, and one Lagrangian for most stuff. And I don't believe you can read that. I'm sorry, but I wanted to include everything, and that is just clearly too big. Now, most people today are working with strings, which is kind of like hair in a way. And what would their shirt look like? Well, here's an idea. And some string person may say an equation to be written at a later date. And there was some stringy stuff that's probably too small to see, or it's hidden somewhere in some kind of dimension or compactification or something. I'm sorry to sound so vague, but it's because what's written on the back is if there was one Lagrangian, well, they'd write it. I could write it. But they're still working on that, so they don't have field equations on the front. So when I look at these competitors, I see two theories that are too small, because they separately do well with, say, light, or they do well with gravity. I see one that's just too big, and one that doesn't even make a shirt. So I think spending 2 more cents on this shirt actually is what a picky little bit should do. Thank you very much.